I'm Callum. I'm a final year chemistry PhD student, and today I'm excited to tell you a little bit about my journey to chemistry and a little bit about my research as a PhD, which is all based on these green rocks shown here, these crystals and these metal balls, and shaking them together. So my research focuses on this section of the periodic table. That's the halogens in group 7. They're a well-recognized group of the periodic table, consisting of iodine, bromine, chlorine, and fluorine, if we make our way from the bottom to the top. And we know that these group 7 non-metals are characterized by their high reactivity. As with 7 outer electrons, they desperately want to gain an electron to achieve a full octet. They are often characterized by their colors, and some halogens get a bit more attention than others, notably fluorine, which is the 9th element, existing as the stable isotope with mass 19. We heard a little bit about isotopes in our previous talk. Fluorine, as I'm sure you're aware, is the most electronegative element. So it gains an electron either by forming a covalent bond, a shared pair of electrons with another atom, or by removing an electron from another atom to form a fluoride anion. But before I go into why I became fascinated by fluorine, I thought I'd start by telling you a little bit about why I became fascinated by chemistry overall. And that starts by kind of tracking back to where I'm from. I'm from a small town called Dudley in the West Midlands. It's the heart of the UK. It's a small town near Birmingham, but also close to Wolverhampton. So Wolverhampton is well known for its football club. Unfortunately, my Dudley accent has disappeared over the last couple of years. But when I was much younger, when I was a teenager, I was actually interested in cookery. So I didn't really know anything about chemistry or science, but I really enjoyed cookery. And so I wondered if I could sort of pursue a career down that route. Having said that, I was definitely fascinated by science and natural history to some extent. But when I was choosing a career pathway around the age of 16, university wasn't really an option that I had in my mind. Neither of my parents had gone to university, so I didn't really think of it being an opportunity for me. So following on from my kind of love for cookery, I decided to study food tech as part of my A-levels, which also expanded onto maths, biology, and chemistry. So I was sticking in with some of the sciences. And it was really when I was at sixth form that I kind of developed a real love for chemistry. Chemistry is everywhere in our lives, from the food that we eat to the batteries that run our laptops and our smartphones. And it was this kind of importance of chemistry in everyday life that inspired me to pursue it further into undergraduate studies at university. So I decided to embark on a master's degree at Imperial College London. And it was really there where I learned chemistry is more than just learning it from a textbook. You can really apply it to make real-world impact. And a turning point for me came when I moved out of the UK. I hopped across the pond to Europe to work in Switzerland. And there I undertook a year-long internship at a pharmaceutical company called Roche, where I worked alongside a team of scientists to develop and design new drug molecules using state-of-the-art synthesis for anti-cancer medications. This internship also gave me a unique insight into what a career in science could potentially look like. So we've kind of come a long way from just, oh, is university even an option, to actually working in the chemical industry. A kind of important point with working in the pharmaceutical sector was I first developed an understanding about fluorine. So fluorine is an atom that is prevalent in many drug molecules, including drugs that help lower our cholesterol. It's important in molecules that help combat diseases and viruses such as COVID-19. It's also important in imaging. So medical imaging relies on another isotope of fluorine, fluorine 18, for PET imaging of internal organs to enable diagnosis of illnesses in patients. And it was this kind of importance of fluorine that motivated me to pursue a PhD in fluorine chemistry. I was really interested in developing new fluorination reactions and new fluorine methodologies and applying them to the synthesis of drugs for healthcare. And I was inspired by the outstanding research of Professor Veronique Governeur here in Oxford and her team's fearless and cutting-edge approaches to innovate new fluorine chemistry that is used in industry and with researchers across the world, around the world. But fluorine is also incredibly useful in other aspects of our lives beyond just healthcare. You may not be aware of this, but at least 20% of agrochemicals used to make fertilizers contain at least one fluorine atom. Fluorine, some of you may be a bit more aware, is also used for refrigerants and coolants that help keep our food and medicines cool. I think most people probably associate fluorine with dental products and toothpaste, where fluorine is found often as metal fluoride salts like sodium fluoride. Fluoropolymers like Teflon are really important in our non-stick cookware, in packaging, and also raincoats and umbrellas. And I think perhaps less obvious is the role of fluorine in everyday electronics. So all of the smartphones that you have contain fluoride anions and fluorinated anions, which are used to make the batteries and the electrolytes in those products. And actually, fluorine in electronics is going to become more and more important as more people turn towards electric transportation and demand more devices like smartphones and laptops, etc. But a key question that was proposed to me when I joined Oxford by Veronique Governeur was, where on earth does all this fluorine come from? And it's kind of a strange question, because I guess we all use things in our daily lives, but maybe not think about where do the actual atoms that make up those products come from. And it was here that I realized, or found out rather, that fluorine in all of the fluorochemicals that we use in every day comes from chunks of salt called fluorspar. So these chunks of salt that you can probably find in jewelry shops or museums, a bunch of it is mined across the world for the use, for its fluorine content. And in this fluorospar, the element fluorine exists as fluoride, and it's bound to calcium. So many of you will recognize calcium fluoride, which is a strong, which features very strong ionic bonds. It's an ionic lattice, and it's the strength of these ionic bonds, these ionic interactions between calcium and fluoride, that gives calcium fluoride a high lattice dissociation enthalpy. That's the amount of energy, or the energy required to dissociate 1 mole of this calcium fluoride lattice into its constituent ions. I'll talk a bit more about that in a moment. But how do we turn these rocks into our batteries, into our fluoropolymers, into our medicines? Well, first the fluorospar crystals have to be mined, and then they're converted downstream into the fluorochemicals. But to do this, we require some chemistry, some pretty old school chemistry that was first discovered and reported by Swedish chemist Carl Wilhelm Scheele around 200 years ago. Now, for well over 200 years, the first step in accessing all of the fluorochemicals is to convert this rock, fluorospar, into hydrogen fluoride gas. This is done using sulfuric acid at 300 degrees, so pretty harsh reaction conditions. If we look at this reaction a little bit closer, take calcium fluoride, it's got a high lattice dissociation enthalpy, it's strong, doesn't react with anything. And we take sulfuric acid, highly corrosive. You can see here someone's pouring this, it's a liquid at room temperature, pouring out without a glove, which is just pretty crazy, I wouldn't advise that. But nonetheless, it's this reagent that is required to harvest out all of the fluorine from the calcium fluoride rock in the form of hydrogen fluorine gas, which is highly toxic and corrosive. The side product of this reaction, or the byproduct rather, is calcium sulfate, which some of you may associate with gypsum, which is used in the construction industry for plaster production. So when people think of fluorine, I think most people think of fluorine gas, which is this yellowish gas, again, highly dangerous, very oxidizing. This actually comes from HF. through a process called electrolysis. This reaction was developed by Henri Mouzin, who's a very famous fluorine chemist who's won the Nobel Prize for this work. Indeed, both HF and fluorine gas are very dangerous. Fluorine gas can actually eat through glassware, so I would not recommend using that. Nonetheless, today, industry still relies on the conversion, the central result process of fluorospar to HF, which is either stored as a cooled liquid, so you take the gas, cool it down, and you store it in canisters, or you dissolve it in water as hydrofluoric acid. It is then transported around the world for subsequent usage. And chemical manufacturing plants take the HF and they convert it into the fluorochemicals through a manufacturing process, either through forming fluorinating reagents like fluorine gas, or other more easy to handle fluorinating reagents like potassium fluoride, which is a widely used fluoride salt. Nonetheless, these reagents are still very dangerous. HF burns. HF is an extremely dangerous molecule. There are actually precautions and restrictions put in place to even use this in the lab. Some of you may associate HF with the show Breaking Bad, where Walter White actually uses HF to dissolve bodies. If you spill HF on your hands, it will penetrate into your tissues, destroying your tissues. It will also decalcify or strip your bones of the calcium. It dissolves glass as well, so it has to be stored in very specialized containers. And HF in the news has also gained some notoriety. Unfortunately, there have been multi-ton spillages of HF, which have led to widespread detrimental damage to farmlands, towns, and in some cases even killed workers that work with HF in these factories. So considering the safety challenges and the hazards associated with HF, when I started my PhD, the problem that was put in front of me was, well, can we just bypass this whole process, go directly from rock to fluorochemical? Bypassing HF and accessing fluorochemicals directly from fluorospar would represent a cheaper, greener, and safer way of doing fluorine chemistry, with enormous benefits also on the carbon footprint, considering the amount of transportation required to get HF from the factory to the fluorochemical. So this could also be more environmentally friendly than the current supply chain. The problem is that this is really challenging because these rocks do not dissolve in anything. The only thing they react with, well, up until now, was sulfuric acid. So how do we harvest the fluoride anion from fluorospar? Well, as I mentioned, ionic solids usually dissolve in solvents, like water. And you'll be well aware of this because sodium chloride, which is taken as the typical ionic compound, exists as a giant ionic lattice where this ionic pattern of sodium and chloride is repeated across the lattice. And we know sodium chloride dissolves in water. Now, most ionic solids are soluble in water because it really depends on whether the attractions or the energies between the water molecules and the ions are large enough to overcome the attractions between the ions themselves in the actual lattice. Another way to think about this, which some of you may be familiar with, or at least coming on to, is to look at the energy changes going from that solid to the aqueous solution of sodium and chloride. So the entropy change, just to reiterate, to convert 1 mole of the solid crystalline lattice into its gaseous ions is the lattice dissociation energy. And we can represent these energy changes on a Born-Haber cycle. I promise this isn't too complex, but I will go through it step by step. So the lattice dissociation enthalpy for sodium chloride is about 780 kilojoule per mole. This number varies slightly dependent on textbooks, but nonetheless it's always around the same order of magnitude. The amount of energy released or absorbed when these gaseous ions are put into solution is known as the enthalpy of hydration. Usually the enthalpy of hydration is separate for each ion, so sodium ion and chloride ion. Here I'm just summing them together. And finally, the enthalpy change of solution, that's taking the solid 1 mole of that solid ionic compound into a solution, in this case is about 10 kilojoule per mole. It's endothermic, which means when you dissolve sodium chloride in water, it actually absorbs some of that thermal energy from the surrounding water. So great. What has this got to do with calcium fluoride? Well, calcium fluoride is also an ionic solid, but it doesn't dissolve in water. If you take calcium fluoride and put it in, it's just like sand. So it just sits at the bottom of the flask. We can do the same analysis of the energies, going from calcium fluoride, the ionic solid, into its constituent ions. Now we have a dissociation entropy of 2,602 kilojoule per mole. This is much greater than what we saw with sodium chloride. Again, the hydration entropy, pretty large. It's on the same order of magnitude as the dissociation entropy. And finally, to complete the cycle, the entropy change of solution in this case is slightly exothermic. So now, to dissolve calcium fluoride into water would be minus 60 kilojoule per mole. But we know that this does not happen at room temperature. The take-home message from all of this is that if we look at the magnitudes of the dissociation enthalpies of the lattices, sodium chloride's lattice dissociation enthalpy is really just a fraction of the larger dissociation enthalpy of calcium fluoride. And that comes down to the electrostatic interactions between the ions in the lattice. Fluoride is much smaller as an anion and has a very strong interaction with the calcium. And so the take-home is that the lattice enthalpy is greater for calcium fluoride than sodium chloride. So, with this in mind, how do we release the fluoride from calcium fluoride to do chemistry, other than boiling it in sulfuric acid? Well, I think you'll probably be aware of this. Behind every single reaction, there is a driving force. If a reaction, for example, is exothermic, we take reactants and they convert into more thermodynamically stable solids or products. That's the driving force that drives the reaction, that enables it to be spontaneous at room temperature. So with this in mind, our lab came up with an idea, came up with a hypothesis. Perhaps we could generate a compound that is more stable than the calcium fluoride itself. In this way, we could release or liberate the fluoride to do fluorine chemistry and form a calcium salt that is more thermodynamically stable, i.e. has a greater lattice enthalpy than calcium fluoride itself. And the salts that we chose to look at were calcium phosphate salts. So you've already heard from Amy a little bit about teeth and bones, which do indeed contain collagen inside, but on the outside surface of these bones, there are key minerals that are mainly composed of calcium phosphate. Calcium phosphate is a super strong solid. It's highly insoluble in water, and that's a pretty good thing, because otherwise our bones and our teeth would just be crumbling right before our eyes. With this, we are probably also very aware that calcium phosphate minerals are used in everyday processes. So in the morning when we brush our teeth, we're actually incorporating fluoride into our tooth enamel, which is made of calcium phosphate minerals, to form very strong bonds between those fluoride anions and the calcium in our teeth, and that's important for preserve tooth enamel. So with this kind of thinking in mind, with fluorine, calcium, and phosphate, we targeted phosphate salts. I do appreciate that calcium phosphate may look a little bit complicated as a salt, but I can assure you it's not. It's simply just comprised of 3 doubly charged, positively charged calcium cations surrounded by 2 triple negatively charged phosphate anions. And the phosphate actually has this tetrahedral geometry that some of you might be aware of, where the phosphorus is in the center of that anion tetrahedron and then surrounded in the corners by the 4 oxygens. So phosphates is what we need. But which phosphate would we choose? That was another key question of this. There are numerous different metal phosphates that exist on Earth. And after studying and investigating a wide number of phosphates, the one that turned out to be most optimal was this salt here. So this is dipotassium hydrogen phosphate. You may not be familiar with it, but it's actually a commonly used food additive. So it's really safe. You can even buy this off, apparently you can buy this off MyProtein, and it's used in the fitness industry. Dipotassium hydrogen phosphate, in this case, if we react it with calcium fluoride, we could form potassium fluoride. If we take the potassium and the fluoride. We remove that fluoride from calcium fluoride. We form potassium fluoride, which is a much more soluble source of fluoride. You can see that in the lattice enthalpy, 808 versus 2,602. And to complete our reaction, we would also form calcium hydrogen phosphate as a very stable driving force for our reaction. So that's great. Well, that sounds great on paper, but how do you actually put this into a reaction? We still have the problem that calcium fluoride is completely insoluble in all solvents, including water. But doing chemistry in solvents, which is the traditional way chemists have been doing chemistry for thousands of years, is not the only way. And it might not even be the best way of doing chemistry. It turns out that you can actually just grind these two salts together. So we remove the solvent completely. This is a particularly interesting endeavor, especially for chemistry, because now we don't rely on solvents. It means that you can take any solids, grind them together, and that opens up a lot of different possibilities for chemistry. It does sound a bit voodoo, and I will admit when I started this project, this just sounded a bit strange to me that you can grind two solids together, but I can assure you it works. So the type of chemistry I'm referring to here is called mechanochemistry. It is essentially the chemical transformation promoted by the absorption of mechanical energy, either by compression, by shearing, or by friction. So just grinding these solids together. And in doing so, you increase the surface area, you reduce the particle size of your rocks, for example, you increase the surface area, and you also increase the number or the frequency of successful collisions between the ions in these two lattices. This chemistry is super simple, and to show you how simple it is, I thought it would be worthwhile to actually do some right here. So if we have a volunteer that would actually like to grind up some fluorospar, that would be very, very helpful. So is anyone keen enough? Your hand went straight up. So you seem to be very, very keen to do some mechanochemistry. So please pop down. I will get you some gloves. What's your name?
Molly.
Molly. Yeah. Molly, nice to meet you. There you go. And these are medium gloves. I hope they fit. So to start this chemical reaction, we're actually going to take some fluorospar. So unfortunately, you probably can't see this because it's absolutely tiny, but this is some fluorospar that I tried to grind earlier today. Molly's going to carry on grinding this to start our reaction. So if I leave you to grind that in a pestle and mortar, it's the same way that we grind spices in a pestle and mortar. Now, if Molly was to stand there and do that, she would probably take the whole day just grinding those cells together. So Molly, you can stop. That's fine. A more sophisticated way of doing mechanochemistry is a process known as ball milling. And this is a very kind of new technique that has emerged in chemistry. Essentially, instead of standing there and grinding, as Molly would have done so, you can take these solid reagents and put them into a jar, a metal jar, with a ball bearing. Now, ball bearing is nothing special. You can just buy this from a bike shop. So, Molly, if I ask you to prepare 2 samples. So these are the jars. Inside there is just a ball bearing. This isn't a magic trick. This is just chemistry, unfortunately. So if you place a scoop of the fluorospar into the jars, and we also have some potassium phosphate salt that I weighed out earlier.
Is it just in this?
Yeah, just in there. So if you put 1 scoop of that, and then 1 scoop in the other, then drop in the phosphate.
Can you do that?
That's not, yeah.
Yeah.
Thank you. Cool. So we've taken our 2 solids. We have fluorospar crystals, which Molly has already started to grind down, and we also have our phosphate salt. If you close these together, so that goes with that one. I can do this one. So it's very safe chemistry, unlike the sulfuric acid route. We're both just doing this here. And it's very simple as well. And if you can put these into the ball mill. Cool. That's perfect. Thank you. That will just tighten that. Cool. Thank you. So what we are going to do here is grind the two solids together in the ball mill. And the ball mill frequency, that is how fast that jar moves in the machine, can be tuned. And how fast we shake that jar is proportional to the energy input that we put into the reaction. So if you just press the plug here, put it on. Cool. I'll turn the frequency up. Oh, turn it too down. There we go. And if you can press start when you're ready. Can stop that. So usually when I do this, it's done for about 3 hours. It drives everyone nuts in the lab. You can take your gloves off. You are done for now. So that's the reaction. Can we have a round of applause, please, for Molly? So, as I said, usually we would leave that on for around 3 hours. That was like, 10 seconds? So there might be some reaction happening, but we would leave that for longer in the lab. So it's simply that the mechanochemical activation of calcium fluoride occurs by adding that phosphate salt, ball milling these salts together, causes the ions, the fluoride, the phosphate, the potassium, and that calcium to exchange with one another. And this is an example of an ion exchange reaction. And the powder that's in that machine right now is a white solid that we called fluoromix. We had no idea what it was, and we had no idea what to call it, but it made sense to call it fluoromix, fluorine mix. The important thing is that this powder contains fluoride ions that we can use for fluorination reactions. So if you remember, calcium fluoride doesn't react with anything, can't be used. The fluoromix can be now added to solvents, so it actually dissolves into solvents. And this has been simply achieved by just grinding it with the phosphate salt. In this case, the solvent that I used is an alcohol solvent, butanol. Features this quaternary carbon center surrounded by these 3 methyl groups in the alcohol group. And if to this reaction we add a haloalkane as a reactant, we can do a fluorination reaction to form a new carbon-fluorine bond. To look at this a little bit closer, some of you may recognize this as a substitution reaction, a nucleophilic substitution reaction. Just as a kind of little reminder, we have fluoride in the system, which exists as our nucleophile, the electron pair donor. We have our haloalkane, which is the electrophile. The electrophile bears partial positive charge at that carbon next to that electronegative bromine. The reaction occurs such that the lone pair of the fluoride attacks into that carbon adjacent to the bromine. The curly arrows represent the movement of the electrons, and the bromide is released as a leaving group with the formation of a fluorochemical, featuring a new carbon-fluorine bond. So that's just one example of a fluorochemical we could make using fluoromix. In my PhD, I actually prepared over 50 different fluorochemicals. Some of them are important in battery applications. Some of them are important in the synthesis of drug molecules like Lipitor. Others are used for antibiotics. And finally, I was also able to make fluorochemicals that we could use to make fertilizers like indaziflam, which is one of the most widely used fertilizers globally. Importantly, all of this fluorine chemistry and fluorochemicals were made bypassing HF entirely. So that's a real strong advantage of this type of chemistry. So to kind of finish off this part of the research, a key question is, well, what's in fluoromix? What has it converted into? And how is it even doing fluorination chemistry? Now, to understand the structure of a chemical or a compound, we can turn to the electromagnetic spectrum. So many of you may be aware that we can use radiation. When radiation is passed through a compound or a molecule, the bonds in that molecule absorb some of the radiation and some of it is transmitted. And the amount of energy that's transmitted can be used to figure out what's in that chemical. We use this, for example, in infrared spectroscopy, where we use IR radiation to look at different bond stretching frequencies. And we can also use nuclear magnetic resonance, which relies on radio waves, to determine the connectivity between atoms like carbon bonded to hydrogen, etc. But how about a crystalline powder? How about a crystalline salt that just contains anions? Well, there's another technique that you may not be aware of, but you would certainly learn more about in a degree in chemistry, and that's a technique known as powder X-ray diffraction. So it relies on high intensity, high energy X-rays to figure out the structure and the constituents of that crystalline powder. So to give you a very brief insight into powder X-ray diffraction, essentially it works by shining X-rays directly onto the powder of the substance you're interested in. Importantly, X-rays are just high energy wavelengths of light, and they have these periods called wavelengths, which are so tiny they're on the same order of magnitude as the distances between the ions in the ionic lattice. X-rays, when they hit the lattice, they are diffracted, i.e. they are bent from their original path when they interact with the electron density in each of the ions in the crystalline lattice. And the X-rays that are diffracted, they're measured, they're recorded, and they're graphed. So what we get out of the diffractometer, which is the machine used to do X-ray diffraction, is a plot like this. And that graph, or that plot, is closely related to the atomic structure of the powder. This technique is nothing, it's a very precise technique, but it's actually widely used. So it's not specific just to this type of chemistry. It's widely used in materials chemistry, in physics. And here we specifically used it to work out the type of crystalline species in fluoromix and the distances between the atoms in the solids. And kind of similar to IR spectroscopy, you can match that fingerprint pattern to a pattern that's already been recorded by other scientists in the world. And you can match that, and in doing that, you can kind of play snap with two different diffraction patterns to figure out, well, what's in the compound. So the diffraction pattern of fluoromix is recorded. It's this black pattern shown here. Here's the samples of fluoromix. You put them on these little plates, and then they're like, go straight into the diffractometer, where the X-rays are then emitted onto the sample. And as you can see, the diffraction pattern just contains a load of peaks. It's quite, looks quite complicated, and it was really complicated, actually, to try and figure out what was in here, because unfortunately, these peaks did not match to anything in the databases or with compounds that had been recorded previously. One starting point, though, is that if you see some of the peaks, they actually match to the diffraction pattern of calcium fluoride. So that's great. We've got one of the kind of starting points of the puzzle here. That comes as no surprise, because we started with calcium fluoride when we started to make the fluoromix. It turns out that through almost 2 years' worth of testing and making lots of different salts, we found one salt does match with some of the peaks in the pattern of fluoromix, and that's this salt here that I just called X because I had no idea what it was or what to call it. But it turns out it's this tripotassium hydrogen phosphate fluoride salt, which is a really important salt because it's actually the main reactive component of fluoromix. The other peaks match with another compound which is somewhat more complex. It contains potassium, calcium, a monofluorophosphate unit, which is this PO3F unit that bears a phosphorus-fluorine bond, and phosphate as an anion. With all those pieces of the puzzle together through this kind of detective Agatha Christie style of analysis, we found that fluoromix is comprised of two different salts, X and Y, which up until now had never been discovered previously. So we may actually be the first people to ever even discovered or seen these salts and learn about their fluorinating ability. So to summarize, the process that I discovered alongside my team in the Governor Group is as simple as shaking some fluorospar with phosphate in a jar with a ball. And that represents a breakthrough for the production of fluorochemicals, streamlining the current high-maintenance supply chain, which, as you saw, relies on sulfuric acid and HF gas. I was quite pleased to see that our work was kind of positively received by the media. It certainly caught a lot of attention, and I really like this headline, the steel balls instead of poison gas. But I guess it kind of makes me reflect on a kind of broader message of chemistry as a whole. How does this chemistry play into the wider role of chemistry in our future, for example? And as human beings on the planet, we tend to exploit finite resources like fluorospar, which we can mine from the ground. We take those resources and then we do chemistry. We make fluorochemicals, for example, and then we use those fluorochemicals in our everyday lives. For example, the fluorospar was used to make HF. HF was used to make the Teflon pan. Now, in my PhD, together with my lab group, for the first time, we generated fluorochemicals bypassing HF entirely. And although this was an important step, another kind of key factor of this is, well, where do all the fluorochemicals go after we're done with them? Chemical manufacturing processes and technological advances, like the development of smartphones, laptops, have created ample chemical waste, both during and after the production. And that includes fluorochemicals, but it also expands beyond fluorochemicals. It also includes plastics, the toxic metals used in our smartphone batteries. And unfortunately, it's beyond nature's capability to deal with this waste and break it down into useful materials to help kickstart this process again. Unfortunately, most of the chemical waste is burnt into CO2, which just worsens the ongoing climate change crisis. So, chemistry and science is screaming out for creative, smarter ways to convert waste into useful starting chemicals, thereby creating a circular way of doing chemistry, which would reduce our dependency on these finite starting materials, preserving the planet for future populations. When I started my PhD, many of my friends, students, and colleagues thought that the idea of converting fluorospar into fluorochemicals was just ridiculous. They even thought it was impossible. And many industries and research groups across the world had tried to formulate solutions to this problem, albeit unsuccessfully. However, I decided to take a risk when I sort of chose to follow this through with a PhD, because I thought there was something quite exciting about shedding light into dark areas of chemistry that people were too scared to look at before, or that were kind of unknown previously. And I think that's really where we, or rather new scientists, can shake up solutions to chemistry to solve scientific challenges. With that, I would like to end. I'll certainly say that doing a PhD has been a very exciting and rewarding part of my life, full of unexpected science, but also a lot of cool discoveries. I'm currently actually in the last 2 weeks of my PhD, so I'm finishing. And here are just some of the memories from my PhD photographed. That's my lab group at the top there. Veronica's hiding somewhere in the back. I've been fortunate to travel around the world to present my research at numerous conferences with my friends. And finally, I've had the privilege of meeting many amazing scientists, including Nobel Prize winners. With that, I'd like to say thank you to your attention this evening. Thank you to Professor Gouverneur for the opportunity to work here in Oxford, my lab group, my family for putting up with me, and my collaborators. What I didn't mention really is that this research requires extensive collaboration, a lot of different ideas and thoughts from numerous scientists, both here in Oxford and around the world, actually. So thank you for that. And finally, I'm very happy to take any questions if you have any. Thank you.